Welcome guys to a new video. This one's about derivatives, exam question. So here's what we have. Let y equals ln x over x to the power 4, x is greater than 0. Question A, show that the derivative is as follows. So what do we have here? Ln x over x to the power 4. We could say ln x is a function f of x, and then x to the power 4 is another function g of x. You guys should have on your formulas, on your formula lists, that f of x divided by g of x derivative is as follows: f derivative of x times g of x minus f times f of x times derivative of g of x divided by g of x to the power 2. So let's apply this. We're going to take the derivative of the first, multiply with the second, and see. So let's apply this formula to our context. So let's apply this formula to our case. F of x is ln x. So I'm going to write ln of x derivative times g of x is x to the power 4 minus f of x is ln x times g prime x is x to the power 4 derivative over x to the power 4 to the power 2. Let's continue. Ln x derivative is 1 over x times x to the power 4 minus ln x times x to the power 4 derivative is just 4x cubed over x to the power 4 times 2, which is 8. Let's continue. Let's do some simplifications. So we're going to have here x to the 4 and x. We can simplify by x. We have 1 here and x cubed over there. So now we have x cubed minus ln x times 4x cubed over x to the power 8. And then we can have x cubed as a common factor, x cubed times 1 minus 4 ln x over x to the power 8. And then we have x to the power 3, x to the power 8, we divide by x to the power 3, we have x to the power 5 over there. So now we have 1 minus 4 ln x over x to the power 5. This is the derivative that we had to prove, so we are good. Question B. Consider the function defined by f of x to be ln of x over x to the power 4, and the graph is y equals to f of x. The graph of f has a horizontal tangent at point P. Find the coordinates of P. Alright, so when we have a non-linear function, such as in this case, whatever the shape would be, I'm not going to try to make the shape accurately, but let's assume this is the shape of f of x. If we want a tangent that's horizontal at a point P, it could be, for instance, here, it could be, for instance, there. So a horizontal tangent implies that the derivative of the function at that point must be equal to 0. So let's do that. Let's use the derivative of the function that we calculated from here. Let's make it equal to 0, and then we're going to find the coordinates of this point, because that's what we want, the coordinates of point P. So f derivative of x equals to 0 implies that 1 minus 4 ln x over x to the power 5 equals to 0. Now we know that division by 0 is undefined, so the only way to make this division equal to 0 is to have the numerator equals to 0. So we're going to do 1 minus 4 ln x equals to 0, which means 1 equals to 4 ln x, and ln x equals to 1 over 4. Now that we have this, we are going to make x the subject. How can we do so? We can do so by using the number e. So I'm going to say e to the power ln x equals to e to the power 1 over 4. E and ln cancels out, and I will have x as a remainder, which is equal to e to the power 1 over 4. So this is the x coordinate of point P. I also need the y coordinate of point P. So the y coordinate is f of e to the power 1 over 4. Remember, the y coordinate is the output or the function value when you plug in the input. So I'm going to put e to the power 1 over 4 into my original function, not into my derivative, into my original function. The original function is this ln x over x to the power 4. So I will have ln of e to the power 1 over 4 divided by e to the power 1 over 4 to the power 4. and now ln and e cancels out, so I'll be having 1 over 4 divided by e to the power 1, since 1 over 4 times 4 is 1. So now I can put this together as 1 over 4e, meaning that the point P has the coordinates with x being e to the power 1 over 4 and y being 1 over 4e. That's it. Hope this makes sense. Let's carry on. For question C, it says, given that second derivative is the following, show that P is a local maximum point. Okay, so how can we have a local maximum point? If I were to assume the graph of a non-linear function, we can have a maximum point looking like this. Okay, meaning that at this point the first order derivative must be 0, second order derivative must be negative. Why is it negative? I'll explain in a second. It is negative because the function is increasing at a decreasing rate. Remember that the first order derivative is gonna tell you whether the function is increasing or decreasing, but the second order derivative is gonna tell you whether the function is increasing or decreasing at an increasing rate or a decreasing rate. A decreasing rate in this case implies that the function is increasing slower and slower. That's why it's flattening out. So if we were to prove that the second order derivative at this vertex point is negative, that is enough to conclude that it's a maximum point. And we know in our case what's the x coordinate at this point, since we have the point P with an x coordinate. We have the point P with an x coordinate of e to the power 1 over 4, this one. And it says in the question, show that P is a local maximum point. So now we're going to plug in the e to the power 1 over 4 into the second order derivative, f second order derivative of e to the power 1 over 4. This second order derivative, we're just going to substitute and see whether it indeed is negative. So we have 20 times ln of e to the power 1 over 4 minus 9 over e to the power 1 over 4 to the power 6. Then we can do some simplifications. We have ln and e simplified. We have 20 times 1 over 4 minus 9 over e to the power 6 over 4, which is 3 over 2. Now this one is going to be positive. Let's figure what's on the numerator. 20 times 1 over 4 is just 5. 5 minus 9 is minus 4. Minus 4 over e to the power 3 over 2 is going to be negative, since the denominator is positive for sure, but this one is negative. We know negative divided by positive is negative. So in conclusion, we can say that the second order derivative of e to the power 1 over 4 is negative. Hence, we can say P is a maximum point. Alright, that was question C. Let's have a look at question D. Question D says, solve f of x greater than 0 for x greater than 0. Okay, well, f of x is the following. This is f of x, ln of x over x to the power 4. So let's solve this. I'm gonna go here somewhere. Question D. And we want f of x to exceed 0 given that x exceeds 0. Substitute f of x with ln of x divided by x to the power 4 must be greater than 0. Since x is positive, obviously the denominator will be positive always. And then we have to make sure this one, ln of x, must be equal, ln of x must exceed 0. We know that if ln of x equals to 0, x should be 1. So therefore, in order for ln x to be greater than 0, x should also exceed 1. So therefore, x must be greater than 1. This answers part D. And finally, let's have a look at part E. Sketch the graph of f, showing clearly the value of the x-intercept and the approximate position of point P. Alright, so we know that P is a maximum point, right? I'm going to try to make a sketch over here. And we also know that we do not have a quadratic function, so we cannot just draw a parabola like that. We have the function ln x divided by x to the power 4. We also know that there is a specific intercept here, namely, if we were to find the x-intercept, so the function must equal to 0. When is this equal to 0? It's equal to 0 when ln x is 0, so therefore x should be equal to 1. Now that means 1 is going to be an x-intercept. And we know that P is a maximum point, and the x-intercept of P is going to be e to the power 1 over 4. E to the power 1 over 4, since e is above 2, and then we're going to raise it to a power, that e to the power 1 over 4, which is the x-coordinate of P, must be above 1. So it's going to be to the right of 1. Let's put it here somewhere, e to the power 1 over 4. And we know that this is the x-coordinate of this point P. So let's say that's going to be our point P, and the point P is a maximum, which means the function is rising towards this maximum. And you have to see what happens to P. Clearly it doesn't go symmetrically because it's not a quadratic function. However, so if we think about each component of this function ln of x and x to the power 4, what happens? What happens is that if you put very large values for ln of x, this outcome will increase, this number will increase, but it will not increase towards very large numbers. Whereas if you put x to the power 4, well, even if you put 10 to the power 4, that's already 10,000. Imagine if you put 100 to the power 4, that's an absurdly large number. So what's gonna happen is that the values are gonna be dropping very fast because the denominator will exceed the numerator by far. So the function, the graph after the point of P is gonna start dropping very fast. Dropping, in other words, at an increasing rate. So it's gonna look something like this. So our graph will approach the x-axis as x increases towards infinity. Hope this all makes sense, and we are done. I'll see you in the next one.